landscape for sorry, got it. Okay. Is this what is happening? I think it's moving. Anyways, so this is not playing. Where you go? So wildfire, what was I saying? In terms of motivation, yes. These wildfires have been part of the natural landscape for a healthy ecosystem, but I think we all agree that they're projected to become more frequent and intense due to changing weather patterns and anthropogenic activities. So the video on the right shows the Marshall Fire that happened about a month and a half ago in Colorado, just in December. And these fires are not limited to what we define as the fire season any longer. So existing wildfire risk assessment procedures rely primarily on exposure and historical data to prioritize wildland-urban interface communities without assimilating the community response. The existing tools cannot be used to evaluate the effect of different mitigation or preparedness actions. Some of these mitigations I have here as an example in terms of management of fuel breaks close to the community, distance between the buildings, fire rating of different construction types, vegetation around buildings, and so on. So we really don't have a quantified measure of the effect of such activities. So that brings us to the research objective, which is to simulate being able to simulate the spatial and temporal behavior of wildfires in WUI communities, considering uncertainties and community characteristics. So our team so far has developed the basis or version 0 of what we call SWIFT, this is the Streamlined Wildland Urban Interface Tracing. In this code, the fuel types, we have 3 types: structures, vegetation, and non-combustible, basically ponds and streets and so on. And we capture fire spread based on radiation and fire spotting. Fire spotting, these are the embers that can fly and land on a fuel bed. It can be a vegetation, again, it can be a building structure causing ignition. And in terms of the temporal and spatial scale, we're looking at model gets updated every 5 minutes, scale of 10-meter resolution. And the overall philosophy is to combine physics and theory with observations and data at the same time capturing the uncertainties. So this is one application of the model to the community of Fountain Grove, which was affected during 2017 Tubbs fire. This is part of Santa Rosa, basically. And this simulation is gonna start, there you go. This is ignition. These all yellow means ignition in structures or vegetation. And the key here is that you see these fire lines, and these are jumps because of the embers, fire spotting, and then because of close distance between the buildings, radiation takes over and causes the fire to spread among the buildings. In this case, the fire destroyed the whole community. So where we're going next with this SWIFT code and how to improve, there's this Dean's data set collection of damage, basically after they do inspection after wildfire events by CAL FIRE. It contains more than 76,000 structures. And we want to adjust the ignition criteria and code based on the type and characteristics of the structures and eventually quantify the effect of these characteristics on the behavior of the overall community. So in summary, and the challenges we're facing, in the long term, why are we doing this? Because again, looping back at the beginning of the presentation, for mitigation, we can use such a code to identify vulnerable parts of the community and improve the resilience. For preparedness, we can optimize resource allocation in terms of how many fire engines and what locations and so on we would need. And in terms of response, this code is quite fast. It's a matter of seconds to minutes to run to decide if the fire can be suppressed or not based on the rate of fire spread. At this point, the decisions are on ad hoc basis and experience of the fire chiefs. And the challenges, these are just a few, there are many challenges, but we would need detailed data on fire propagation inside communities. And right now we don't have such temporal resolution in the data. Example from satellites, we typically get fire line before and after they touch the community. And then it's very hard in the fire community to do large-scale tests. It's for safety reasons as well as cost reasons. So we don't have an understanding of the combined effects of different measures that we can take and how they would impact, again, the response on the community level. And finally, another challenge is that capturing or establishing models to capture fire spotting different phases in terms of generation, transport, and ignition from these embers. So quite a complex process, and then merging them within these community level studies, that's another level. So thank you for, again, this opportunity.
I'm going to talk about post-earthquake community functionality analysis model that we developed recently. So as we know that functionality is typically measured by the ability of infrastructure and building system to serve its intended purpose, but we have recently noticed that recent disaster causes severe functionality losses despite the improvement of buildings' physical performances as well as construction practice. This is partly because the current building code heavily focuses on protecting the life safety, but do not specify the requirement of reducing functionality losses. Also, to resume normal activities and access to emergency and essential services, road network accessibility to building is vital, which is often ignored in recent studies on functionality analysis. So in our functionality analysis framework, we developed the functionality analysis model for buildings that not only incorporate the physical performance of buildings and availability of utility service, we also consider the accessibility to road network. At the same time, we consider the changes in demand on infrastructure system, particularly for water network, due to household dislocation as a result of building damage, as well as interdependency between water and road network. So this helps us to understand utility service availability more realistically, whether building is receiving utility service or not. Our framework consists of 4 modules. Using a scenario earthquake hazard analysis module, we estimate first the seismic intensities for buildings and infrastructure components. Then using existing fragility curves and stochastic damage realization, we assign the damage states to buildings and infrastructure system. At the same time, we consider geographic interdependencies to see whether water and road segments are co-located physically. And then after knowing the physical damage to buildings, we estimated the changes in demand on infrastructure system for hydraulic simulation of water distribution network. Then we, once we know the performance of the network and buildings, we estimate the functionality of buildings based on physical operability, whether the building is having lower level of damage, as well as utility availability, water and electrical service. And then we estimate the access to road network, considering the assertion matrix method in graph theory. We use that, and for individual functionality performance of infrastructure system, we used topologically based performance measure to measure their performance throughout the restoration process. So after the damage, immediately after the disaster to the full recovery state, we perform stochastic simulation of each component using the existing mean repair and restoration timeline from the literature. So we applied this framework for Centerville virtual community that consists of buildings, power network, water and road network. So we assign the physical damage for electrical, power pole, distribution substation, as well as pipelines, elevated water tank. And for road network, we estimate the damage for bridges. So once we know the earthquake intensity, we generate random number for each component to assign physical damage to the infrastructure components and buildings. Then we also estimate the interdependency between water and road network using GIS buffer analysis. And based on the ratio of physically operable buildings, which changes on the demand for water network for demand nodes. After we perform the analysis, we develop the building portfolio function portfolio curve for different building cluster, and we have noticed that consideration of interdependency, utility service, and physical accessibility significantly alters the performance of building portfolio, particularly initial stage of recovery. And from the right to curve, you can see that the effect of interdependency between water and road network, as you can see from this red two line, shows the damage of bridges in the road network. So this is the failure of road network itself. But when there is a nearby water pipeline fails beneath the road segments, then road segments need to be closed until the pipelines are repaired. So we consider the interdependency effect, and we have noticed that consideration of interdependency significantly changes the performance of network that need to be considered for the functionality analysis at the community level. In conclusion, we tell that we consider the coupled interaction between buildings and infrastructure system in our model, and we particularly incorporate the road network physical accessibility in this network, this analysis. And the biggest challenge, I would say, that each network and community have sufficient resource of recovery, we assumed in our analysis, but that might not be the case when we consider the real water road and transportation network. And for this network to execute, this framework to execute, it is very computationally expensive. So particularly a big community is composed of hundreds of infrastructure components and buildings. So to handle this scenario, we developed a Python program to solve this. And the largest problem is obtaining the infrastructure network characteristics and building inventory that is not readily available. So this is our framework, and I will be happy to looking forward to talking to interested collaborator. And I'd like to thank our funding supports coming from NIST and NSF for this research project.
I'm a computer science assistant professor here at ECU. Today I'm going to talk about my research about the data regression for time series data with extreme events. So what is our motivation here? Our motivation here is about extreme events. By saying extreme events, I mean the thing that doesn't happen a lot, like a flood, like a drought, like a hurricane, even like a stock market crashes. Those events, they don't happen a lot, but can have a huge impact on our daily life. And also those events, their data distribution usually is very different from normal events, right? So if we can predict those extreme events, especially here we focus on the time series data, we can save lives and avoid damages. Okay. So what is the problem here? Currently, we try some physical-based model. We work with the hydrological people. We try their physical model like a PRMIs. I'm not sure if you heard this model before. This is a physical-based model. Basically, we'll split the study field into cells and then calibrate the parameters in each cell for the forecasting. Those models doesn't work very well. For example, here, this is the a graph from the PRMS. As you can see, we have orange line and blue line. Orange line here is the ground truth, which is the observed stream flow of a water set. Excuse me. And the blue line here is the error of the PRMS model. When is kind of the ground truth here is kind of very flat, then PRMS does a very good job. The error is kind of like close to zero. That is good. But when we have some peaks here, those peaks here, then the PRMS makes a lot of errors. Okay, those errors you can see. So here we can treat those peaks as kind of like extreme events. Usually we don't have those things, but suddenly the data kind of increase or decrease, then those are kind of treated as extreme event period. And we find similar things with machine learning based models here. Recently, those deep learning models quite powerful, can outpower than the traditional classic machine learning models like the tree-based methods here. We tried those machine learning models. We have found similar things. I'm going to show you some results later. So this is the problem we try to solve. If your time series data has some extreme events here, how can we accurately forecast those data for those, for example, like the peak part here? Okay. So this is our proposed framework. The key idea here is we want to give machine learning models some ideas. We have some extreme events here and there. Please pay attention over there. Those can be different from other parts of your data. But let's say that we organize our original data like a matrix, time series data as a matrix here. Of course, if you have a multiple research set, it can be a multi-dimensional array, it can be a three-dimensional array. But let's just simplify the problem as a two-dimensional array here. So the rows here represent the time step. The columns here represent the variables you have. Well, you may have a nitrogen, stream flow, conductivity, those type of values here. So together we got a matrix. And we are going to do data pre-processing to mark which one here can be treated as an extreme event. So those data pre-processing methods you can choose based on your own data characters. For example, we use the SPOT here. SPOT is an algorithm from a KDD conference. That is algorithm help us detect which one is anomaly one. Okay. So let's try to say that, okay, here we use a green to represent the normal events and the red represent the extreme events here. Then we can have two possible ways to give the machine learning model hints, which are different from others. The first one is we can use the extreme event split the pipeline. This is kind of like a manual way. Basically, we split our data into two groups based on those vector we found it here. The vector shows which one is normal, which one is extreme, right? And then we train two different machine learning models here to generate a prediction. And then after we got those predictions, we're going to combine them back together for the target variable. Okay, that is one way. This way is kind of like a not part of the machine learning procedure. It's just manually tell machine learning model, okay, those are two different group of data. By using this way, it can help, but it may break the temporal information here. Okay, for example, this you want, the next one is this red one. But if you split it here, you connect this one with this one. So you break the temporal information here. Sometimes it doesn't work that well. That is reason because of this, we propose another way here called the matrix, mass matrix pipeline here. So for this one, we're not split the data into groups. Instead of doing that, we create a mass matrix. Instead of this matrix, we highlight which part of data machine learning model you should pay attention here. We're going to change the weights here. If you are known ones, then we're going to label you as 0. If it's extreme ones, then we're going to change the weights here. We're not going to mark it 1. We're going to use a percentile here to mark how extreme the event is. And then we combine this mass matrix with the original data, input a machine learning model. Then our model can learn what's going on here and generate a better prediction. Okay. To prove our idea is working, I show you some of the results here. We have more results in our paper. If you're interested, you can read our paper. This paper is already published in the IEEE Big Data Conference, one of the top conferences in my domain. So we try the stream flow data prediction here for 3 different watersheds. And the base means this is the original GRU neural network. And the SPOT and the percentile, this is the two extreme event split pipeline. I hope you still remember that, basically this part. And the mass means this is the second pipeline, mass matrix pipeline. As you can see, I highlight the better results here with the bold font size. Most of the time, we got the mass matrix with the better results. Okay, so that's all for my work. If you're interested, I'm happy to answer any questions. Thank you all for being here.
Minutes, I thought I'd put as much context in there as possible and just get right into it. So in my field of estimating flood risk, probably the most commonly used tool is this class of functions called depth damage functions. They're generally made available by FEMA or the United States Army Corps of Engineers. And the general idea is that depth, the flooding depth that a structure faces, explains most of the loss associated in a flood. This hasn't really been empirically validated in like the academic literature that extensively because those observations are so hard to come by. Fortunately, we had access to around 700,000 after filtering observations of loss that were appraised from floods over a 40-ish year time period of 400-ish events behind the National Flood Insurance Policy flood claims. So exploring this is depth sufficient question, just using a simple general additive model for different quantiles of loss, and on average, we're just exploring is depth a sufficient statistic. You can see that there's a lot of variability around the mean at different depths based off of the empirical data, and that variability increases as hazard gets worse. So that motivates this question in the academic literature on what other attributes of structures or hazard help you predict this very variable process. The key constraint is when you're trying to estimate flood risk over large scales with a single function or maybe like a similar class of functions, you don't have that much access to many, many variables or very complicated model structures. So there's a trade-off between the model complexity and how well you might be able to predict your outcome. So we use those 441 events in a leave one out cross-validation setting to control for event-specific anomalies, spatio and temporal variation from event to event, and explore various sophistication and complexity-based models, starting with kind of the benchmark FEMA or Army Corps of Engineer models linked where the loss occurred to what FEMA region they're in and a damage function that might be made for that FEMA region, and then variously more complex types of empirical models. The key result that I want to draw your attention to is that we have generally unbiased but kind of imprecise estimates of both relative loss, which is the kind of percent damage from the slide before, and then that scaled by the structure value, so for total loss. So that is not really distinguishable in a meaningful way across the models. What is important is as the hazard gets worse, these models all perform less reliably, even if they're pretty much mean unbiased. And then they start distinguishing themselves in the tail of value. So the most valuable homes have very different quality of prediction depending on the model complexity and sophistication. That could have a lot of implications, these very high depth homes, very high value homes, when you look at an extrapolation over a very large scale. And so that's what I want to focus on. So I used these stratified GAM to add a little more context. They're like the Army Corps of Engineer depth damage functions in that you only need to know if the home has a basement, how many stories it has, but they're empirically fitted for that depth damage relationship. So just comparing these two very easy to implement interpretable functions against each other, you see an implication of twice the amount of expected annual loss every single year. When you have major disasters, you might be underestimating loss just based off of the damage function that you're using. And so most of that is because of these very low depth homes. Actually, what happens is when you go from modeled depth to the first floor elevation that you use in a depth damage function, the empirical function and the Army Corps of Engineer function make very different assumptions about what you do with low depths in basement homes. And some of the average losses that you get to the no basement homes with a little bit of flooding. That's where the majority of this divergence is generated. And because of the distribution of those depths and structures, you see pretty big differences in the Midwest and the Southeast. So I'll stop there and could go into a lot more details in the breakout if anybody would like to talk about that.
Okay, so this is heat stress impacts in South Florida. And can you see my full screen?
We're seeing it in, now we can see it.
Now, okay, thank you. So my research is on subjective heat stress impacts in South Florida. And I'll begin with introducing the hazard as such. It's a heat risk is a risk of immense inequity and uneven burdens. For decades, the deadly and catastrophic risk made worse by climate change has been part of the lived experiences and struggles of low-income communities in the developing as well as the developed world. It's a silent and invisible risk for several reasons. Heat illnesses catch people unawares and quickly escalate to fatalities, are often or underdiagnosed in hospitals, and most significantly, heat risk is disproportionately borne by low-income communities, communities of color, and marginalized people. And for these reasons, heat risk has failed to get the attention it deserves from public health and policy. While extreme heat is commonly identified with heat events, in subtropical and tropical regions like South Florida, heat is a slow onset risk, chronic in nature, and sustained all year round. Climate change has, of course, made it harder, and Florida is projected to experience about 150 days per year of a 105 degrees Fahrenheit heat index by the end of the century. And disturbingly, heat research has indicated that beyond mortality, heat affects health, productivity, and the overall quality of life and well-being of people. So we, in our research, given the high income inequality and racial diversity of South Florida, we investigated the differential impacts of heat stress on people's health, well-being, and productivity across several socioeconomic factors, and especially the nature of their work. We've used surveys online as well as face-to-face to gather the perception of heat stress and basically asking people whether they're feeling the growing heat. Our conceptual framework posits the plurality of heat stress experience, not only through physical and emotional impacts, but through cognitive performance. We posit that heat stress is influenced, of course, by socioeconomic, environmental, and behavioral factors, but it is manifested through several daily life activities, as well as through absenteeism and presenteeism at work. The results analysis is still ongoing, but in our survey with farm and outdoor workers, we found that approximately 72% have said that they missed work because of heat stress, and more than 80% have experienced low productivity, during which time their percentage of impaired productivity is also 80%. We have estimated the economic loss to farm workers at about $576 per year per worker, solely because of impaired productivity. And a structural equation modeling also indicates that heat stress, health conditions, and heat-related protections impact the life satisfaction of these farm workers. In our general tri-county-wide online survey, we found that people across the board, respondents who work outdoors, who do high levels of physical work and report missed work days and low productivity, are also affected by heat stress at home while doing errands, outdoor exercise, etc., but also in their physical, emotional, and cognitive performance and health. In the next steps, what we are trying to do is identify an array of heat adaptive measures, nature-based and community-based solutions for South Florida, proposing an implementation plan based on equitable adaptive finance measures. We are proposing to advance a governance framework from scaled heat adaptation solutions, a framework to facilitate transformative strategies for economically sustainable, ecologically sound, and equitable and just outcomes. Thanks to all the funding support that I have. And with that,